Okay, good afternoon, and well, depending on where you are, good morning, good very early morning to some of our European colleagues joining us today. Wherever you may be, welcome to this session. My name is Graham Williams. I'm Chief Scientist with the Software Innovation Institute of the Australian National University. It's my pleasure for this session to welcome you to our first of two very special keynotes for the applications track within DSAA. Our speaker today is John McLoone, who is the Director of Technical Services, Communication and Strategy at Wolfram Research Europe. Wolfram, of course, many of us know of Wolfram over very many years, and they've been a leader, of course, in developing software to support computational intelligence and, of course, Mathematica. John will be sharing opportunities that come with the multi-paradigm approaches. Over to you, John.
Thank you very much. Okay, well, let me start by just extending that introduction a little bit and saying that for those of you who don't know, what Wolfram really have been doing is building a big technology stack for 30 years to automate computation, and so that finds its way into consumer things like Mathematica. But is also behind Siri, Alexa, and Microsoft 365 doing knowledge queries. And so I have that technology background. I want to sort of talk about the philosophy that we at Wolfram have been pursuing with the way we go about computation and how that affects data science. But it's also colored by my experience. One of my roles is to lead the consulting team in Europe. And so we're out at the coalface, taking out the Wolfram technology and applying it to various, mostly data science problems for external customers. And so I want to share also some of the practical experience of what this sort of philosophical approach of Wolfram means to actually doing work. And I've got a bunch of mostly toy examples to illustrate that through the talk. So ultimately, the goal of all of this technology is an automated data science workflow. What we want to be able to do is, in the minimum work, take data, do the kind of computational analysis you need to get some insight, and follow that workflow all the way through to whatever the endpoint is, whether that's publishing an academic paper or making an application or deploying some web service. And so while I'm going to mostly focus on the middle data science part of that, the wider story is this whole workflow. Now, here's the sort of central claim of my talk, that the answer to all of that, the answer to joining up workflows, the answer to joining up different kinds of data science, and the answer to automation is surprisingly symbolic computation. Now, anyone who's used our technology, typically the start point is sort of cheating on the maths homework at college, or solving some differential equations or equations in a physics class, and that's people's most contact. So when they think of symbolic computation, typically they think of things like doing an integral, and instead of having to numerically sample that, let's do something like this one, you get a symbolic response back. Computer algebra is what most people think of as symbolic computation. But from our point of view, symbolic computation is much more abstract. Computer algebra is just simply one application of the idea of representing things as symbols. So to show why that's kind of important, I want to kind of go back to a very simple example. So still in the computer algebra space, I was trying to think what's the kind of lowest level operation, and a change of variables is what came to mind. So I've got some symbolic expression, and then I've got a replacement that says wherever we've got x, we're going to replace that with u minus 1, and we get some new symbolic expression. So we've got symbolic expression in, symbolic expression out, and some operation that applies that. Now that, again, looks like computer algebra. It is computer algebra. But fundamentally, the fact that this happens to be an algebraic expression is irrelevant to concepts like replacement. Behind the scenes, this algebraic expression has this symbolic representation in terms of it's a product of something that is a power of something that's a sum of two things, and it's got this kind of serialization which represents the same thing as this. And we happen to know within the system, we've taught it what times and power and plus mean. But these symbols, time, power, plus, they could be anything. They just happen to be things that we know about in this context. So if we look at a completely different context, a more data sciencey thing, then data cleaning is exactly the same kind of operation. I've got a list of data here, and this is a real example I had where the customer is using minus 9999 to represent missing data. And we can take that data and say, okay, here's our rule now to do replacement. Anywhere that you see this minus 9999, we believe that to be the symbolic value missing. And so this sort of data cleaning operation is conceptually exactly the same thing as the computer algebra operation. And in fact, we can go into any domain we want, and replacements has a kind of equivalent concept. So here's something not at all like computer algebra. This is some polygons representing a 3D scan of my face. I guess if I moved in line, you'd see it was me. And I can apply exactly the same kind of operation of saying, well, everywhere you see triangles, replace those with lines. And now what we've got is a wireframe version of my face. Now, the crucial thing here is that I haven't had to invent some new language for data cleaning or for transforming 3D CAD data. As soon as you can represent something symbolically, then this replacement operator can work on it. So we've got one command that applies in this case, 3 different contexts automatically without having to worry about what kind of data it was. As long as we've got a representation of the data, whether it's polygons, lists of numbers, or computer algebra, as long as we can represent that symbolically and we have a symbolic programming language, we can operate on it in a totally unified way. And that turns out to be a pretty powerful and very extensible idea. So if you look at the way Wolfram language sees various expressions, we've already saw the behind the scenes of some maths. And then we had I had a 3D graphic, didn't I? So there behind the scenes, it's got a symbolic wrapper graphics 3D that tells us what kind of thing it is, and inside is a list of edges and triangles and so on. But we can extend this idea to things like hierarchical key value data sets. So here's a multi-dimensional key value structured data set out of a database, and it's got a symbolic representation, so we can operate on it. Things like metadata, which I'll come back to a little bit later in the talk. Here I've got 4 different kinds of 2, but they're different because we can symbolically represent that the first one is a round to 1, which is giving error bars on that. The second one is a quantity in meters. The third one is mixed quantity of 2 foot 2 inches. And the last one is a date in a certain calendar system with a certain display format. And as I said, this extends to lots of things. We can talk about graphs, images. These things all have serializations. And you'll see in this talk later on, things like programming code and complex models like neural networks all have symbolic representations. Even this interface I'm clicking, this little tab view that I'm clicking around in the notebook here, that has a symbolic representation, as does the whole document. That in this case is a tab view of some images. So ultimately what this means is that when you're within the Wolfram language, all data is the same. In the end, it's all a symbolic object. And there are different ontologies that we might think, different operations apply to images than apply to maths. But fundamentally, the data structure that we have in the system makes everything look the same. So what symbolic computation is, it's not computer algebra, it's this idea of a unified representation of structure, data, and meaning. That when I have something like 2 meters, I've got the data in there that it's 2, I've got the structure that it's a quantity, and I've the structure that, in fact, in this case, very simple. It's got 2 parts: a quantity and a magnitude, and the meaning that it's a physical quantity. And that applies to all of these different things. That as soon as you've got the symbolic object, you have all 3 in one place. And very often that's one of the challenges when you do data science is you get the data, and in your head is the meaning, and the structure is typically something unhelpful like a rectangular array because you've got the data out of a SQL database or out of a spreadsheet, and you have to think about how you mesh the meaning to the structure as you do your work. And that's all work before you even start doing the data science. Now, I said that one of the things that we want to do is to automate. And symbolic computation is this underlying representation we have actually is a key enabler for automation. That having a richer representation of the input, so we know what it means, not just what the numbers in it are, and rich representations of output, so we can pull together different concepts and represent them in a consistent way. Those are the key things that make it possible to inject automation on top of the actual algorithm itself. So let me show you a couple of examples here. Let's do a little bit of classic machine learning. So this is my favorite classic data set. This is the passenger list of the Titanic. We've got some input here. First class, so traveling in first class, 29-year-old female, and she survived. And you can see already that we're getting some of the benefits of the symbolic representation, is that we've got a little bit of structure in this data set, that we've grouped together a list of 3 inputs against an output, and then we've got a list of those. So we actually got a kind of multi-dimensional set that has also in it, if I'm just scrolling around here, we'll see the symbolic representation of some missing data in places as well. And my task here is to try and predict what would happen if I were to travel on the Titanic. So I'm going to make a classifier function, and our task here is classification, and I'm going to classify that data. So because the system can look at that data and understand what the things in it are, immediately we get some automation in terms of it saying, okay, we can recognize that there's a category, a number, and a category appear to be going on, that it's a list of 3 things, and it's conjured up a serialization to turn that into the vectors necessary to do machine learning on. But behind the scenes here, you see that it's, my task was classification. I didn't say an algorithm. What I said was a task. And in fact, there's a dozen standard machine learning algorithms built into this classify function. And it's decided for itself that that the best method to use was naive Bayesian. And then it's returned this very rich, complicated object that wraps up the model, the training values that were learned, the encoder and decoder, so that I can take that and give it some data. So I would clearly travel first class. I am 50 and male, and we'll get our prediction out that I would not have made it. And if we drill into that a bit further, probabilities, then we can see that according to this model, not terrible odds, but yes, definitely against me by a few percent. Now, the ability to use this thing like a built-in function is dependent on the ability to wrap up everything we need to know into a single rich, complex object. And in fact, if I show you what's on the inside of this, it's kind of horrific. You wouldn't really want to code it by hand yourself. So I didn't want input, I wanted input form. So instead of seeing this pretty little lozenge here, we can see the actual internals of this thing, stuff that I could type by hand if I had a lot of time, but it's constructed this complex, rich object. But that is what makes it possible to the automatic selection, because if it had decided it wanted to use a different method, and I'm going to force it now, I'm going to say method goes to gradient boosted trees. Well, because that object is so rich, we can represent now a completely different internal structure, but externally it's just a classifier function that this time is in method gradient boosted trees, and will presumably give me a somewhat different, okay, that's given me a much more pessimistic view on my odds. Possibly an inappropriate method, or possibly that's just a consequence of different methods and it's equally valid. So one of the things that it then does is it elevates this automation to conceptualization. As I said, I didn't put in the method, I put in the task. And that can make these tasks actually very broad. So here's a sort of different kind of problem, computer vision. And I'm going to try and recognize the difference between cars and tanks. So I've got some training data, some cars that are labeled car, and some pictures of tanks that are labeled tank. And let's just run that through the task and apply it to some unseen test data. And when it's had a chance to think about this, there's about 60 pictures in the data set. It's just doing a bit of pre-processing on. Hopefully we'll get our answer in a few seconds. But even though this is conceptually a little bit different, it's computer vision rather than classifying number, category number type data. The task for me to be able to apply it here is still just classify. And that can work because with this symbolic representation behind the scenes, the image, it knows that's an image, and it knows that there are certain things it can do to images, such as the way that you might um, serialize that to vectors to pass into an appropriate training method. And something's clearly gone wrong here in this example. I'm just going to cancel this and try again. Yeah, something has failed. Well, obviously that shouldn't happen. And it looks like something is locked up on my computer, so I may just have to do something different here. Yeah, something unfortunately has crashed. So give me a second here and I will kill that. And go again. Oops. And now I've launched in an unreleased version of Mathematica, which is going to be even less wise. Let me open that in the right version. Okay, here we are back again. Let's just try this one more time. Hopefully I haven't ended up with something pathological about this example. Okay, there was obviously something corrupted in the data that it now says that I've messed up the example. Something in this attempt to compress the data has upset it. Oops. Maybe I should just abandon this example and do something different. Yeah, somewhere probably. Oh, there's the error. I've got myself something that is not in the right format. I've got some nulls in the data that I've actually left in that are not input-output pairs, and I should have done some data cleaning. Probably copying and pasting some things badly when I set the example up. Did I leave any more in? Okay, it's thinking now. Okay, so lesson to self, test examples before talks. Okay, so here's our application to the unseen data, and you can see that it's classified the first 4 as cars and the last 4 as tanks. But the fact that it just switches context to computer vision without me having to reconceptualize is one of these benefits of this sort of super focus on automation, so that we can just do the right thing according to the kind of data that we've got. Now, in examples like classify, it's automation has really obvious benefit for low expertise people, and once you can conceptualize the thing just as classification, if you could just get the concept of whether you want to predict or classify, then the rest of the work is done, and you don't need any expertise to work with it. But actually, I think automation is just as powerful and important for high expertise users. Obviously, there's a benefit to automation that you can save time and effort. But actually, being able to work at a much higher conceptual level because of automation allows you to do much more sophisticated things. So I wanted to look at a kind of ascending level of automation within a much more demanding task, which is if you actually need to do kind of proper machine learning and you're going to start architecting custom neural networks, you would think that's now definitely well beyond the beginning user, and automation would is a toy that would disappear. But let's look at how even within those kind of tasks, symbolic representation helps. So first of all, it allows us to talk at a much higher level. And this is true about all kinds of things. I'm not dealing when I had images with matrices of RGB values. I'm dealing with an image. I can just put an image into the input. And in fact, I don't have to worry about whether it's RGB or CMYK images or whatever, because that can be automated. Here is, at its very simplest, a simple neural network model. And the symbolic representation allows me to sum up all of the essence of this without any of the details. So I can say it's a chain of 3 layers. One is a linear layer 20, so a fully connected layer. One a element-wise layer, injecting some nonlinearity into it with a tanh operator, and then a linear layer 1 to bring the points together, an encoder and a decoder. And I'm going to initialize that with some random numbers. So that's all I need to specify in order to spell out a simple neural network. And here's the kind of pictorial representation of it. But again, internally, the model is actually quite rich. It's already been able to automate a lot of the inference of dimensionality. The net initialize has filled in some initial weights and biases. All of the kind of connectivity between the layers, that's all been filled out for me. So I could type this in by hand if I really wanted to deeply specify it, but that's really quite a cumbersome task. But the actual structure of the thing conceptually is incredibly simple. It's just a 3-layer network. So we can separate out detail from the mechanics and just focus on the conceptual side. When we launched 30 odd years ago, Steve Jobs had a nice quote for the box, which was that he was talking about education, and he said it would revolutionize education because it would allow you to focus on the prose of mathematics rather than the grammar. And that still holds true, I think, for even much higher things that aren't really maths anymore. So here's what you do with it. You give it some data. In this case, I'm giving it some values of sine, and then you can train the model. So, again, we can automate, what layers need training and which don't, and how the gradient descent is done, and when the stopping conditions, those can all be automated, or I can specify them in detail if I want to. But at the top level, conceptually, I just say train the network, and here's my network trained to approximate the sine function. So that's the basics of our kind of symbolic representation. What does that give you as an expert? Well, I thought I'd do 2 much more sophisticated examples to show kind of suddenly how things that are quite expert level operations become relatively simple by being able to handle this thing just as an object. So one is network inspection. We run a repository, the Wolf Neural Network repository, where I can download 100 odd models. So I'm just going to grab one of those models out of the system. And this is now a much more rich model. So here's the representation. There's about 20 layers in the outer net chain, but inside that you'll see actually some of them are graph layers. So this layer 3C actually itself has 20 layers within it. So there's about 200 layers in this network, and its job is to do image identification. So I can give it a picture of a tiger, and it returns tiger. I'll talk about this thing that comes back a bit later, but it allows me to do things like say, well, what do you mean by tiger? Let's have a picture of a tiger, and here's a generic picture of a tiger that it's able to map up, because this thing isn't the word tiger, it's a symbolic representation of the concept of a tiger. Now, one thing you might want to do is to, if you're an expert, is try and start understanding how this thing is behaving. So we might want to kind of reach in and grab the weights or biases at a particular layer, or some other kind of inspection. Well, this thing here, it's a symbolic object, so it's just like any other kind of data in the system. It's just like that list of numbers that I had right at the beginning that I did the replacement on. And I can do operations on this just like any other piece of data. Data and code and models, they're all the same thing. So I could say, let's just take the first, say, 5 layers of that network. Oops, got the @ sign in the wrong place. Actually, if I do this separately, you'll see that what I've got now is a new neural network that is only the first 5 layers. So just like I could take the first 5 elements of the list, or first 5 rows of a matrix, or first 5 rows of an image, I can take the first 5 layers of the network and apply those now to the tiger. And what I'm getting is a bunch of matrices. That's not very useful, so I'm going to visualize those by turning them back into pictures. And let's adjust those for brightness. And so here's what we're seeing now is what's going on at each of the different layers at layer 5. So each of the different convolutional layers that has a different thing looking for a different feature. Early on, these are probably looking for features. So this seems to have picked out some strong vertical lines. This one seems to have picked out a very strong horizontal line. Maybe that's the features that those particular networks are looking for. As we get a bit deeper, then these things become a bit more conceptual. This is some kind of combination of features. By the time we're deep into the network, I know layer 15, then we got things that are probably more related to concepts like this pixel represents the amount of animalness of the contents or whatever. So we can, because the thing is data, the contents is data, the stuff flowing through it is data, it's all just there to play with, just like any other data set. Now, another task that is sort of reasonably advanced is to do something like transfer learning, to take a rich network that has been already trained on some other scenario and reapply it to a new scenario. And there's a bit of code in this one, but I'll walk you through it. It's fairly straightforward. What I want to do is I want to take that classifier that we just looked at and teach it to recognize rock, paper, scissors. Now, ultimately, what I'm going to do is do net surgery and then a very customized training exercise on it, and that will give me the task that I want. So the net surgery is actually very similar to what I did before. I'm going to, let's have a look at the net again and explain it. One of the crucial things of this network here is that down at the bottom, the last two layers are, it says here, linear layer, size 4315, softmax layer 4315. So what that represents is softmax is a probability layer, and the 4,315 classes are the 4,315 types of thing that this network understands how to recognize, one of them being tigers. So what I can do is I can drop the last two layers of that network, the things that customize it to the task, and join on a new chain that I'm going to specify, which is just like the simple network I did at the beginning, some two new layers, so a 3-layer, because I've got 3 classes I'm interested in, rock, paper, and scissors. And I'm going to replace the softmax layer back the way it was, but this time it'll infer its dimensionality to give me a 3 size softmax layer. And then I've got a net decoder that says I've got 3 classes to interpret those numbers that come out into 3 classes. And then I've got some training data here that I captured of about 100 pictures of me playing rock, paper, scissors to the webcam. And then we got the net training, which is almost like before, but being an expert, I'm now going to get involved in the details. And I'm going to say the only layer I'm going to train is this new one layer, this layer I've just added. Don't forget anything you've learned about the features of tigers and cars and buildings and things the network knew about. Only learn how they map to this 3 new classes. And it's saying every other layer, don't change at all, just remember what you've got. So here it is busy learning. This is the loss function falling. Here's the error rate on the examples that it's already seen, which is a pitifully small data set. So it's already reached a point where it can recognize the things it's seen before accurately. But that's the beauty of transfer learning, is that you don't need such big data sets because the network has already been trained on 250,000 images from the real world. So I'm getting a bit bored of that, so let's stop it early and hope that that's good enough after a short training round. And now if I take the network that I've just created and attach it to the webcam, so it's a little bit smaller. Now let's not make it so big. So hopefully you can see that in the corner of my screen here, that if I hold up my, oh, I'm on a different webcam, that's not going to be problematic. See if it does that, rock, paper, Says, okay, did okay, despite the fact that I obviously was cheating before by trying to have a constant background, but it's managed to learn enough to be able to do that task in a new context from that from the examples that it was given. But ultimately, although this was a complicated line of code here, it still is only basically a long line of code, about 4 lines or 5 lines of real work on screen, because we can talk about this net at a much higher level. Now, I said at the beginning that what we want to do is to automate data science workflows. There's a lot of different workflows. There's lots of data cleaning, and I'll show you an example of that in a few minutes. And there's lots of different kinds of deployments, whether you're kind of automatic report generation, symbolic representations of documents out there, or app building. And I thought I'll do one example here. And unfortunately, because I crashed earlier, I need to rebuild the example I was going to deploy, which was that that example from Titanic. So I need that data set back again. And that had data in it, and that's what I need. And so this is our kind of, in our compute, develop, deploy cycle, this is our compute section. We've brought our data in, cleaned it, done our analysis, got our classify function. We now want to develop that into an application and deploy it to users. Well, it turns out symbolic computation and representation helps a lot here as well. So I can make a user interface by saying something like a form page, and I'm only going to ask one thing here, which is what's the age of the passenger, and we can assume that they're a first-class male. Save me a bit of typing. And so we're going to have the classifier function, which is going to be a first class of that age person, and make the male. And let's get the probabilities out again. And that's a function, and that's it. So I can represent the idea of a user interface as this kind of symbolic wrapper that's a form page, and then all of the automation kicks in to say, well, numbers, input fields are good for putting numbers in. If it was multiple choices, maybe pop-up menu would be better. And it gives me something where I can type in some number here and get my answer. And let's make that a bit more attractive by making that a visualization of it. And I guess we want some labels on that chart. And here's my user interface. So I put in the age of my passenger, and I get out a chart of their survival probabilities. So that's my develop phase. And I've got this simple representation where the details are of the internals of this can all be computed for me with a symbolic representation. And then the next step is to share this with the world. Now, because everything that it depends on has a representation, that the interface has a representation, the model does, all I need to do is to copy this to somewhere that can interpret it. And I need to give one extra bit of information here. Permissions goes to public, because by default, it will be private to me. So we can copy that now over to a server that's running in the US. And if I now open that in a web browser, the interpretation will be different, because now it has to be computed into HTML and JavaScript. But because the representation has all the information needed, that computation can be done on the fly to make this interface. And in a web browser, I can type in my number and hopefully get my visualization out deployed to the world. And if you went there right now, you could use this example that I've just created. URL. And we can give you a short URL for that. Oh, need to be in quotes. Right. So if you go back later and watch the video, type in this URL, and you'll be able to go and play with that app. So the whole cycle from getting from the data to a deployed machine learning thing is, in the end, can be automated all the way through step by step. So this kind of unification of data, everything's the same, with enough automation to understand the ontologies of what's different about an image, what's different about a sound, what's different about computer algebra, actually unifies all of computation. If you look at what I've been doing, every single thing I've done is essentially some function of a symbolic value returns a symbolic value. And that means that every function can join up as long as there's a way to interpret the symbolic value appropriately for the thing you're doing. You know, you have to think about whether finding the shortest path that is meaningful within a graph actually has a meaning within a sound. It may not conceptually make sense, but if there's conceptual meaning, there's no reason why you can't make that automated. So this leads me to kind of the ultimate consequence of this, which is that our view on data science is not limited to this kind of the narrow paradigms that most people think of with data science, that data science generally falls into camps of there are people who everything is a machine learning problem, other people where it's all essentially classical statistics. Our idea is that you can apply computation to data. And computation is this broad superset of things that includes stats and machine learning, but also all of these other kinds of areas like network analysis and random processes and classical image processing and geometry analysis and all of these different things. And by having a language where these things join up, it means you can apply everything you want to any kind of data. And you know, the key thing here is that that unified computation doesn't just give you a toolbox of all these different types of computation, it joins them up. So here's something that I think of as a data science, but doesn't look at all like kind of standard data science is, you know, we've got data, which in this case is an image, and then we want to get some insight from it. Well, to me, that's, you know, that's the purpose of data science. But in order to get the insight that I want here, which is that what would happen if I dropped a rock into the Great Salt Lake, then in fact you have to touch very different kinds of computation. So I have to do some image processing to clean this image up. I can then move from that into a geometric representation, something more like the 3D scan of my face, but this is a 2D geometric representation of the Great Salt Lake. And from there we can do kind of applied maths problems like working out the eigenmodes of a surface according to the wave equation. And here's where the kind of biggest standing waves would land in the lake, or we can just solve the wave equation with some initial boundary condition, and there's waves rippling out as they would from this impact in the bottom left corner of the Great Salt Lake. Now, that's pretty kind of far from data science, but even for more regular data science, what this does is it changes your attitude to data science. It, instead of trying to figure out how do I clean this data so that I can do statistics on it, or so that I can do machine learning on it, it becomes a question of what's the most interesting thing that I can do that will give me an insight from this data. That you want to fit, you want to choose the tool that suits, that gives you the insight, rather than trying to fit the kind of insights you're seeking to the tool that you have. It's an overused adage, but it's quite true about if all you've got is a hammer, everything looks like a nail. When you've got a wide enough toolkit, then you have a lot of choice, and that gives you kind of fresh insights. So I want to go through sort of what I think that kind of attitude does to data science. So the first thing it does is, even if you are basically in a kind of statistics mindset, actually having this wider tool set unlocks more things to do statistics with. So the two examples I have here are essentially just, in the end, classical statistics examples, but we can do stuff to get more interesting information out of the data. I'm going to redo this here because I haven't got, after I crashed, I didn't have the data in memory. So I've just loaded here. This was a project I did with my daughter. She was writing an essay about Lord of the Flies. And being a kind of mathsy, computer sciencey person that she is, she said, I want to do something that's more than just commenting on the words. Is there something we can do mathematical? So we sat down and we did a basic word frequency counting, and we could see here that where the main characters in the book appear, that the two lead characters sort of jostle for attention in the book, particularly later on, where the book's largely about Jack in the middle and largely about Ralph towards the end. And then you've got this mythical beast that appears early on when they're exploring the island, and then becomes central in the power struggle, and then it's not important towards the end of the book. So that was just pure counting. But you know, she was really supposed to be doing this for an English essay, and so the question was, could we unlock something about actually the narrative and sort of tone of the book. And of course, then you're getting into things like sentiment analysis. Well, machine learning is very good at unlocking a bit of information there. So we can grab from our repository a sentiment analyzer and look at the probability of the positiveness of a sentence. It's fairly approximate, but on average, it does a decent job. So we're doing this to all the text sentences and saying, what's the most positive sounding sentence in the book? And it takes a few seconds to go through the whole book. And here's the most likely to be a positive sentence from the book. I hope this isn't a spoiler for anyone. That's not really how the book plays out. So once we had that tool, then you've got a new thing to count. So we just threw that counted data on of a moving average of the sentiment to get a kind of ongoing tone of the book. So it's all over the place from one sentence to the next. But if you do a rolling average of, I think this is 500 sentences individually classified and rolled together, then you end up with this kind of general trend. Shipwreck at the beginning, quite negative. Having fun exploring the island where they meet the beast, quite positive. Fairly neutral. Our hero looks like he's going to achieve something, and then it's got this dark dystopian ending and it all goes rather negative. And that pretty much sums up the book. So it's a little bit of machine learning in that case, mixed with the stats, gives us that simple image. Now here's a kind of completely different context. This is a little bit of work I did for a company doing needle-free injections, and this is a photograph of under a microscope of this of the drug particles shot through the skin. It's actually a proxy for each. It's agar jelly and little nylon beads in this test sample. But what they want to do is to understand the profile of the penetration of the particles. They need to get deep enough for the drug to deliver its therapeutic effect. And when I first met these people, they were holding rulers up to the screen to measure the points, and it was taking ages to process an image. But you know, we understand images. They're just another data ontology, and they come with their own sort of language that doesn't apply to much else. Like we can do a certain amount of edge detection and cleaning, so we can clean that image up. We had a problem that these particles were overlapping, so we said, well, let's measure the distance to the edge of the particle, and then let's find the maximum of the distance from the edge of the particle. And then for these broadly spherical pieces, you can pick out the separate centers of the two overlapping particles. Well, let me just load that image into memory. Here's the code to do it. And so, you know, here's the ontology of images, deleting small components, measuring the distances, finding the biggest centers, and we end up, here's our detection. I put a little white cross on each image. If I can grab that image and grow it, there we go. You can see it's doing a good job of detecting these overlapping images. And once we've got that gives us the XY coordinates. Now we're into a natural space of statistics and doing things like doing slice level averages, or in this case, producing a 3D histogram of the penetrations. Now that's easy because we've got numbers. So that kind of moving from image world into number world suddenly unlocks this nice computable data set that says that, in fact, there's a greater density of particles to the left and right of the center of the target zone, and there are fewer in the center, but they are getting quite consistently deep, which is the kind of thing that they're trying to understand to engineer the product. Now, another thing that I find is that in practical problems is that people often measure something and then their mindset is set by what they're measuring. So you've counted X, and you want to know things like what's the biggest X, what's the average X. Actually, computation can be used to give you completely different viewpoints on data. This is a little bit of work I did for with the supersonic car people. They're making this bloodhound car that's supposed to go 1,000 miles an hour. This is from the current land speed record holder, some data from the Thrust SSC car. And they gave me a bunch of data and said, just show us what you would do with it. So I didn't have any particular remit, and I just played around with this data. Here's two channels. This is the RPM of the front right wheel, effectively the speed, and the front right suspension position that wheel is attached to. So you can see, just by doing straight visualization, you can see some interesting things when it achieves top speed, what the top speed is, things like that. But just by doing a little bit of basic computation on this, you get different ways of looking at the data. So if we do a little bit of calculus on that data, we can take that velocity profile and turn it into an acceleration profile, and suddenly interesting features pop out. You can see the velocity, the acceleration goes up in steps, then there's this general curve, and then this big negative step. And if you throw on the throttle position, it makes sense that basically the driver is putting the throttle up in steps to make sure the car's behaving. When he's confident, he goes full power. Then air resistance builds up until it's not going, it's speeding up anymore. He takes his foot off the pedal, and air resistance is effectively now a windbreak. But a completely different slice showed something that was the thing that surprised them most and got them most excited, which is from this suspension data. I used a bit of maths from signal processing, which is wavelet transforms and wavelet scalograms. So this is a wavelet scalogram, continuous wavelet scalogram of that data. And what it basically represents is time along the bottom, frequency up the side, and amplitude is the darkness. And suddenly you get these two features pop out. And again, a couple of other features where there's a kind of sharp rise in high frequency and a discontinuity, and again later. And I'm not the engineer. They were the ones who said, "Oh, I've never seen that before." You know what that is? That's the top edge of the wheel breaking the sound barrier. This was a subsonic run, but because the top edge goes faster than the car, this was the vibration as the wheel starts breaking the sound barrier, and here after it starts slowing down when it exits the sound barrier again. And we weren't quite sure whether this was the parachute or the brakes deploying at the very end of the run, probably both. Now, another thing is a repeat of the idea that I brought up when we talked about computation, which is that actually doing data science on rich, interesting problems actually requires crossing boundaries. It's not just, do I pick the stats tool? Do I pick the machine learning tool? Do I pick the signal processing tool? But actually, you need to kind of mix things together. And this is a little problem I worked on. Now, the actual problem was customer nudging on a website. So the idea was we want to lead the customer to a specific goal by putting information in front of them, but we don't want to try and get them there in one step. So you can imagine, for example, if somebody comes to a website for bicycles and you want to sell them a Ferrari, there's no point saying, hey, buy a Ferrari. You say you want to buy a car, don't you? You want to buy a nice car. Well, if you're going to buy a nice car, you might as well buy a Ferrari, and you lead them step by step. This is the idea. Or if you want to obscure where they're going, like a political messaging thing, then it's you're leading them in small steps so they don't realize you're leading them to some conclusion. So this is the kind of basic concept. Now, in order to solve this, you actually need to do several things. You need to do some machine learning to build some kind of feature distance measure for the content. What does similar mean? And then you end up with a graph of similarities. And we need to do some graph theory to find the shortest path to the target location on this relationship graph. Now, the example I was looking at was rather boring. So I did a proxy example for talks, which is all dogs lead to poodles. And so we're going to lead people to a poodle by making them look at similar dogs. So it's conceptually the same thing, and the maths is the same, but the context is different. So I've got a data set of dogs. I took just a sample of the Stanford dogs database. And then we've got some machine learning operations to try and extract some features. And we get a vector of about 60 numbers that represents what's interesting about the picture. Then in order to make the kind of graph that I want to solve, I'm reducing the dimensionality down. And there's sort of two things to control here. Is the dimensionality that we can flatten it down to 2 or 3 dimensions. So I've gone all the way down to 2 to really kind of stretch this problem. The more dimensions, the more shortcuts through the middle of the ball of data. And then the other thing we can do is we can punish multi-steps, because we want to make going through 3 nodes more expensive than going over the same distance through 1. And so I'm making the distance function exaggerated so that dissimilar dogs are more dissimilar. So I'm stretching that. And these are the 2 things we can control to decide how complicated or simple to make the graph. And we end up with this is the kind of graph of relationships of the dogs that I picked. And we can then do graph operations now that we've got a graph. We can say what are the 2 most distant dogs that dog 206 and 577, presumably about here and here on the graph, are the most distant. And then we can find that shortest path and build the image collage of the images. So here's our 2 distant dogs, the poodle at one end, and this, I don't know what it is here. Now that doesn't seem to have done a very good job in similarity, so maybe there's nothing like this dog in the set. But then you can see we've kind of gone through a whole bunch of Irish wolfhounds, possibly moving then into Labradors, and then furry Labradors, and then somehow we make the switch into terriers, and then long-haired terriers, and eventually we end up in poodles, and then dark poodles, and we end up with our target. And then we can just compute this for any dog in the data set we want. We could, let's pick a random dog here, dog 123, and recompute from that random dog. If I got the data loaded, hopefully I've not found a dog that's disconnected from the set. It's a Chihuahua I've picked, and then it's got some pointy-eared Chihuahua-like dog, and then that's got into corgis, and actually this is quite a long path, as long as the previous one. And eventually we end up settling back into the same end of the graph. So a data problem, but to solve it, we needed to mix machine learning and graph theory. And so is important when you want to mix human knowledge along with data knowledge. Because sometimes you know something about the physics or the situation, and that injecting that in can add to the data. This is another toy example that sort of crosses boundaries as well, but also is sort of an example of how mixing data and knowledge becomes possible if you've got all the tools in the same system. So this is a sound. It's the sound of a vehicle going past, and our task here is to identify whether to give it a speed ticket from the sound. Now, if we had a whole bunch of these examples, clearly it's a machine learning thing. We can just give it examples of sounds and say that was 40 miles an hour and train some neural network on it. I've only got one sound, so I can unpick part of that problem with a machine learning type model, and there's a nice frequency identifying network I can get, which I guess is meant for musical instruments, but here we can apply it to the sound, and we can see the Doppler shift as higher frequency as the vehicle's traveling towards us and lower as we go away. Now, at this point, we can step away from the data briefly and think about, well, what is the physics of Doppler shifts? And a little bit of time on Wikipedia looking up formulas, and a little bit of computer algebra, and I came up with this formula for the Doppler shift of a constant speed vehicle traveling obliquely to an observer. So that's kind of a mixture of computation and knowledge in order to come up with a model that we can then go back into a stats world and say, can we do a model fit to get that nonlinear curve to match the data that we've generated from the neural network? And then from that, we can extract the parameters from the model, and we see the velocity 20 meters a second, 40 miles an hour, and the distance to observer at the nearest point, 5 meters. But to do this, again, we're mixing computation, and we're mixing things I'm bringing to the party and things the data is bringing. I've sort of really talked about this idea earlier, but I think it's actually, in the end, one of the most powerful things about unified computation is the elevation of concepts. Now, we saw that with the classify function, the kind of auto machine learning, is that we can go, instead of thinking about, nearest neighbor methods or gradient boosted trees, we can think in terms of concepts like classification and allow us to hide from the details. But things that even when you kind of get involved in the details, this elevation of concepts is a real kind of the opportunity that we're trying to drive forward as we go into our next 30 years of how can we take these concepts and elevate them to allow us to talk about problems at a much higher level. And anomaly detection, that sort of first step of the workflow of cleaning data, I think is an interesting recent output of that kind of work. So let's first of all think about this in a simple one-dimensional context. Here's an example of the waiting times for Old Faithful geyser. So if you wait around for 15 minutes, there's a good chance of having an eruption. And what we can do is we can say, well, let's look at those waiting times and find some anomalies. And it says, well, there was a waiting time of 96, 94, and 43 that seem weird compared to the data set. Now, in a classical approach, what you're doing here is you're looking for the tails of the problem. So you would, let's just jump through this code here quickly and see the result. We're finding some kind of model that represents the data, and we're saying the tails of the problem of the model are extremes, that anything that's too far up the tail is anomalous. Now, already we're seeing both a symbolic representation opportunity here and also a problem in this example. First of all, you can see here that I've been able to model this by saying it's not a normal distribution, it's a mixture of two normal distributions. I don't know how they're mixed, and I don't know what they are, so these are parameters. And we can then estimate those parameters to give us this symbolic model. And we can do this because mixture distribution can take symbolic representations of distributions as arguments. So this idea of meta distributions, of which there's a whole bunch, only work if you're if you're in a symbolic world, because otherwise I can only give it examples from a normal distribution, not the actual representation of the normal distribution. And other examples like, you know, what's the fourth biggest out of 10 samples, or what if we truncate this and say time can't be negative? In fact, probably I should have done, because you can't have a negative waiting time. So I should have truncated this between 0 and infinity to make a more accurate model. But we also see some of the problem here that you know, this sort of natural statistician's world of everything in the end is a normal distribution starts breaking down already, that if this dip was low enough, then actually a value here would be anomalous. So it's not the tails that's interesting. It's the height of the PDF. So this is the kind of classical approach of saying, well, what's the probability that given this distribution, we're above some value, and we'll make that the cutoff because that's 3% of the data or whatever. And you could solve that to be 1% or whatever. We've extended the idea of CDFs and PDFs into this rarer probability, which is, if we're going to look at 90, we're looking at the total area that is that likely or less. So it's this area, but it's also a little bit of this area, and it's also this area here. So now the chance that you're going to get something as weird as 90 from that distribution is 11%, 12%. So that's the sort of classical approach. But I promised you here a kind of elevation of concepts. So you know, we started looking at the question of anomalies and saying, well, what if it's higher dimensional? And you can take this kind of concept of tails to 2 and 3 dimensions, but then it sort of breaks down pretty quickly, and you start saying, well, what if we looked at anomalous things that were, what's an anomalous photograph? And you start realizing that actually this is all exactly the same space as I've been talking about all the way through this talk. All data is the same, and we've got this sort of framework of machine learning that knows how to pick out features out of complex high dimensional things. So we can bring that all together in order to make something that takes the concepts of stats and apply them with this new machinery. So here's another classic data set. This is the MNIST handwritten characters. And what I want to do is to learn a probability distribution from that data. So conceptually, this thing is just like a normal distribution. It's a data distribution that takes, that has various possible outcomes that have a certain statistical distribution. But once we've represented this through the machinery of the back end being machine learning, all the things we can do to distributions, like saying what's the probability of something, or let's make some random examples from this distribution, those all just work because it's just a distribution like chi-squared or normal or whatever else. So these things here are not, this is conceptually distinct from synthetic samples that are trying to pass for real. These are random images that have the same statistical properties as the images it's seen. So if a pixel here is dark, then a pixel here is equally likely to be dark, as has been seen through the distribution. So these should be indistinguishable in statistical measures from the background data. And now I can start saying, well, what's the probability that something is as weird as this 8? And 80%. So that's a very typical kind of thing. But once we've got that kind of machinery, then this idea of finding anomalies, well, that just applies. We've got a distribution just like we had in the classical case. We're trying to find things that are in that rarer probability space that is, say, in the 1% level. And we can go through this data set here and say, do any of these things look wrong? And it's picked out this little photograph of something which isn't a digit, can't quite see what it is, it's a bit low res, and this very noisy, there's a digit in the background you can just about make out as a human, but it's being corrupted with lots of noise, and it spotted those and said, you may want to consider these as being anomalous. Now, once you've got that with the kind of everything is the same, everything can be encoded and passed through machine learning, then find anomalies will just work. You just give it a data of any kind. So these, for example, are little colors, they're not even images, these are RGB color specifications, and we can say, look at this list of colors, which colors look like they don't belong, and it's picking out these 3 very bold colors from this pastel collection. We can pass in sounds and text and whatever, and just say, show us the anomalies. And I think that the idea that we can just bring down this very human concept of weird, unusual data that doesn't belong in the data set and make it, broadly speaking, I mean, again, just like the machine learning, there are lots of little details I can control for the more pathological and difficult cases. But the fact that in many simple cases, you can just say, find anomalies as a cleaning step is, I think, kind of an amazing consequence of this tower of technology that we've been trying to bring together. So we're building on higher steps. And I have overrun on time because I forgot a whole section I want to talk about, and I've gone a bit slowly. I think I can spare just a couple of minutes to say that a key part of making all of this work is computable data. We've got to get data into the form that is representable symbolically in a way that follows an ontology. And very often data is down at the bottom end of this, that it's kind of systematically stored and maybe has some structure. But the idea that you can derive properties of the entities, that they're all consistent and the ontologies join up, that is a mammoth task. That is a whole extra section of what we do. And I'm just going to show a little example of this in action and a little glimpse of what's behind the scenes, but I can't spare the probably 10 minutes it takes to talk about this properly. This example I'm doing here, this little snippet of code says, grab from Wikipedia the page about Australia, and then we're going to look through that for things that look like countries. So it's got an entity matching where it can try and recognize words that appear to be countries. And then I'm going to make a list plot of that. And hopefully when it's thought about this for a few more seconds, here's a map showing the countries mentioned on the Wikipedia page of Australia. Now, that's kind of a cute example, but actually to make it work, there's a whole bunch of machinery behind the scenes. So we need to have notions of interpretation. So I can interpret, if I was looking specifically for cities, let's put in London here. Sorry, syntax is incorrect. And get out of this something that is a symbolic representation of the city of London. So it's not the word London. Actually, internally, the symbolic representation is this thing entity, and it's disambiguated. And in fact, there's a dozen Londons in the world. If I didn't use interpreted to ask for the most common, then I would get a disambiguation list that says, assuming you mean a city, but maybe it's an admin division or name, and assuming you mean London, UK, not Canada, Ohio, or one of these other, I guess there's 6 of them. But once we've disambiguated, this thing actually represents a thing in the real world, because we've got the symbolic representation that says it's not just the word London, it's a city of London and this specific London. This thing we can now compute with, and we can ask for information on that, like the properties of London, and these are the kinds of things that we know about cities. Or we could ask for what country is that in. So here's the country of the city of London, and this is now an entity of type country. So we know how these entities join up, and we know things about that, like let's say what's the population of the country that London is in, and get some number out. Or more usefully for this, we can get the shape out, and there's a geo-coordinated version of that. So in order to make this little line of code work, what we've got to do is to have a knowledge base that knows how to recognize the words of the countries. It has to have the natural language interpretation, but it also has to have the whole database to know that that when it gets the country of the United Kingdom, it knows things about that, like where it is on the map. And to do this across thousands of data sets that we have, so that if I was after the counties or the towns mentioned, that those would all appear, or the theme parks or railway stations, or all of these other geographic entities. What are the mountains mentioned? I could get those as little points on the map. To make all of that join up requires this big effort of data ontology behind the scenes. And whenever I do data science problems, this pollutes my way of thinking. Is the first thing I do is to try and canonicalize the data. Can we turn the data that the customer gives me into things that ideally are already in our ontology, but if not, have some kind of symbolic representation that I can layer meaning over the top of, so that when I'm going through, I fetch some data from the database that is the product sales of a company that we know, I can just say, what is the class of product this product is in, so that I can then do aggregation, say, okay, I want the consumer goods versus the professional goods. I don't have to write lots of code, because the first thing we do is make sure we know what the data means, and then this kind of automation that joins up data that makes it possible to do kind of, you know, crazy Wolfram Alpha type queries like cows in the UK as a fraction of the GDP of Australia. I don't know if this is going to work. You know, the fact that we can make things like that work, where it's figured out this is probably symbolically what I mean, and we have all of that information. And I guess if I had asked for a fuller answer to that, I could have got a time series out, because I think both of these things have time series. Let's ask for the same thing in a richer answer, not just this concise answer. You know, knowing what a time series is, so that we know how to align time series, so that all you have to do is do the division of one time series by another, and it'll automatically fill in gaps if one of them is missing a 1990 figure. And we see that. What did I ask for? Cows in the UK as a, so there are relatively fewer cows in the UK than Australia is making money. So either Australia is getting richer, or the UK is getting cow poorer, according to this, as a trend, or possibly both. So I'm out of time, a little bit over time. We still have 10 minutes left to try and take some questions. So let me sum up by you know, bringing together my thesis that I started with, that symbolic computation, even though as data scientists we live in the world of mostly of numbers, actually is incredibly powerful for bringing together concepts and elevating the amount of automation. And in the end, if you can, the automation unlocks the ability to use all of these different computations, A, without expertise, and B, without huge effort, which opens up this new way of thinking about data science, where you can do all kinds of crazy things if they will reveal some useful insight. And that's really the kind of focus I want you to take away from this, is if you could do anything, what would be the insights you would get from your data? And you know, our job is to try and make that vision a reality. We're part of the way there. So that sort of wraps up what I wanted to say. Do we have any questions that I can take?
Well, first of all, thank you, John. That was it was great to be reminded of the simplicity of symbolic language for machine learning, and how powerful that really is. So thank you for that very enlightening presentation. So we do have time for questions, and there are several ways of asking a question. You can click on the little button at the bottom of your screen to put up your hand, and then we will unmute you and you can give your question live. But also you can use the Q&A functionality, and your question can be submitted anonymously if you're a little bit shy, or you can use the chat. So feel free to fire away with the questions. And if I can start off with one, while everyone else is building up their confidence to ask a question. You know, one of the big things at the moment, I guess, is explainability. And, you know, I really like the idea of, you know, we can apply computation to data as prose. But can we get to, or is there something that you can offer around the explainability of, for example, the classifier object entity that you get? You know, I'm thinking of the nature of children to always be asking why do we get that answer, and then iterating over a why type of thing.
Yeah, we haven't taken that on yet. And to be honest, I still consider that in the world as a whole, a fairly unanswered question, because I mean, you know, because of our representation, everything you need for the explainability is in there. And there's some nice work we did with Barcelona on a university on a medical project where they were taking one of the inner layers, just like I revealed with the tiger, the inner layers, where they were monitoring a particular layer and aligning that to this was for cancer detection in colonoscopy, in order to generate a heat map of where the attention was being drawn on the layer, so that they could highlight not just this is being classified as a potentially cancerous image, but to put the heat map over the bits that was driving the probability. The real challenge, though, I think, and the thing I tell people about giving up on explainability is that, what do we mean by explainability? We mean, give me the features that you use to make the decision so that I can consider the features. So in the case of a tiger, it's got a tail and stripes. These are features that we as humans would share with each other. Say, it's obviously a tiger, it's got stripes. So that's the explainability. Now, the reason that works is we have a shared language of features that we have, through our use of English, have agreed that stripes is an interesting feature. Now, the whole point about machine learning in the neural net space is to invent your own features. So it's a bit like asking somebody from a kind of Amazonian tribe who's never had contact with the outside world to explain why they think it's a tiger. They would give you words that would mean nothing to you. Now, maybe those words would represent tiger stripes because they just happen to be a different word for the same thing. But maybe there is something that, because they live with lots of different types of tiger, that there is a particular feature of back arch shape or something that is striking to them because they've seen a lot of tigers. That would be a feature that would be meaningless to us. And I think that's in the end, the space you're in with neural network type things is, yes, you could say it's driven by this convolution. But the fact that there's no English word for the zigzaggy splodginess that it happens to be focusing on means that we can get an explanation, but it's of no use to us as a human in terms of interpretation, because it's just not the way our minds think. So I tend to focus people on, if you want explainability, let's look at sensitivity analysis. Let's look at, in the Titanic example, if I was a year older or younger, what percentage difference would that make to my outcome? If I was in first class, second class, or third class, what percentage? And then for me, at that design point, you can say at least what are the main drivers that would have made a difference, which I find a more useful route to guide people in saying what was the convolution that picked that feature out.